thank you for invitation, and so I have the chance to present my switch. Okay. Yeah. All right. So I talk about my recent work on this Hawking radiation. In this talk, I will try to simplify, provide a simplified version of the quantum mechanical model for Hawking radiation, which I don't really need a horizon, so Peggy is happy. That's me mention about my motivation a little bit. The motivation to come from the couple years ago, 2000, Perry Welch, they have this beautiful paper about this derivation of non-thermal Hawking radiation formula, which is based on the tunneling process. But different from the earlier work is their tunneling process demanding the conservation of the energy, which means the mass of the black hole and the mass of the radiation or the energy of the radiation remain the same during the tunneling. So for that typical condition or constraint, they can divide the tunneling rate as such a formula. And then you can decompose into two parts. The first part is easy to identify. It's a Boltzmann factor, so that's a thermal part of the radiation, which is already, of course, derived long ago by many ways, including the tunneling feature before then. Then the new feature is, of course, the second terms, which come up with this omega squared. The omega is the radiation coming out of the black hole. So this term looks like some kind of like a self-interaction because it's omega squared terms. And of course, this is, you can say this is a kind of a nonlinear, non-thermal part of this radiation. So this is a feature. I will call in this talk and in many other talks, they usually call this is featured emission or featured radiation. Means the radiation has some feature other than the thermal. So usually the thermal means for typical temperature is a Boltzmann distribution spectrum. So you can determine it depends on the spectrum, you can determine the temperature. But here is not just the temperature, maybe you can retrieve something else other than the temperature. Okay, so that's a goal I want to achieve with a simple quantum mechanical model. Okay, so of course, first I want to go look at what happened, as I mentioned, to the Perry-Welch tunneling model. As I mentioned earlier, they have this energy conservation constraint put on this during this tunneling process. And then, so the easy to spot that this factor here is nothing but the change of the entropy. Okay, changing of the entropy during this tunneling process. So, so in that sense, the conservation of this energy, in this case, it happens to be the same as conservation of the entropy. Or you want to say the loss of the entropy, loss of the information equal to the entropy. So you can also say that there is something like conservation of information. So there are a couple of papers, actually a bunch of papers coming out, try to say some story about this tunneling, new tunneling model, which preserve energy and preserve the information, or you say the conservation of the entropy as well. So, so for example, this 2009 group people, they try to define something called mutual information, and then try to argue that during all this tunneling process, you can kind of retrieve all the mutual information by maybe resolve the information loss paradox. And myself, of course, with Jung Hee, and we have also some paper on this, based on this mutual information, and we argue that maybe by optimizing this mutual information, we can show that charge black hole, how the charge black hole radiates. Then there is another paper done with Martino Shogo. He's now in the field, but at that time we have this discussion about this generalized mutual information to empathize entanglement, and using that also to discuss how the black hole information evolve. All of these are basically based on the how do you define information. Okay, so this is I would say this is not really a resolution of this paradox, because all this picture you can see people, well, we play around this entropy change, but we didn't really point out what is the microscopic freedom behind all this information or entropy. So you cannot really say this is exactly resolution of this paradox. Okay, and then of course there's something else I want to highlight. That there's also based on this scenario, people can discuss Raymond as well. Based on this, for example, a couple of papers here, I just point out that you can argue that if you have this logarithm correction to the entropy other than the area low, and then you can using this mutual information argument to argue that there has to be a Riemann after at the finite stage. But of course, you need to first assume that this logarithm correction survive in this UV limit. So as I say, there are also people doesn't like this idea. I mean, doesn't really see to it that this can resolve the paradox. So for example, not true, and there's a bunch of other scientists argue that, for example, this kind of minor or small correction to the entropy actually cannot really resolve the information. And of course, there's a more recent activity initiated by the Polkinski and their group, the AMPS. They have this viral argument and argue that maybe either around near the horizon, you have to give up some of this assumption. For example, maybe the effective field theory fails, or the general relativity, the equilibrium principle fail either way. So there's a bunch of story here. But it's not my point today. Today I'm going to get away of this by forget about the space-time. All right, so that makes life easier if we can do that without discuss the whole equation without the space-time. This is actually motivated by, okay, I jump to the point 2, that there's a paper, Bronstein, maybe it's not called much attention, but because he's working on this quantum information field. And he has a couple of papers. One of the papers he pointed out that if you want to derive the Perry-Welch-Townley rate, which is this non-thermal radiation, you don't really need a space-time. Okay, just based on some argument of this information and making the horizon as some kind of a boundary between two systems, and then conservation of energy or entropy, that would be enough to describe such a Townley rate. So that gives me some idea that maybe I can really do something without the space-time. As I mentioned earlier, I don't think this picture can really resolve the problem, because we don't really point out what is a microscopic free freedom. So can we formulate a quantum mechanical model which has a specific, clear microscopic degree freedom, and also have achieve like Perry-Welch-Townley rate? That's my goal today. So, first observation is as follows. As we usually do in this I would say quantum optics, or this nowadays became popular because you want to manipulate a single atom, and you want to do some trick or play the, like for example, understand how do you compute the quantum computing, for example. You want to trap the atom in that cavity. So the same thing, I want to study a black hole, so I want to trap the black hole in some box. So I will call this box as a cavity. Okay? So imagine that your black hole actually is a Schwarzschild black hole, and then of course this image should be come from curved black hole. It's our universe, most of curved black hole, but just let's assume this is just a Schwarzschild black hole, and it has a runaway property because it has a negative specific heat. So in order to keep a stable or wave can be observed properly, then we keep it in a box and with a refractive wall. So this we have like a cavity, just like this mirror. So the photon can be bounced back for a while before it leak out. Okay, so in this case, I have a well-prepared black hole states I can study. That's just a cartoon picture, but that's a beginning. And of course, this is a version 1. Okay, at the end of the talk, I have version 2, which has a better, after better understanding of this similarity, then I can provide a better picture of this correspondence. Okay, so then I can do. Then I can make some assumption that maybe I can play with this black hole just like I play with this. Usually this in the simple case, this is a two-level atoms. Okay, I can play two-level atoms in the cavity. So here is a story. So then we all remember that in the textbook, Einstein coefficient, AB coefficient, right, describing this spontaneous emission or the stimulated emission. Okay, so this I don't need to mention again. So I have this coefficient called AB coefficient, A and B coefficient, and then Einstein, or you can argue that there's you can compute this radiation rate is given by this AB coefficient, and of course this number of density, state density. Okay, so so then to apply such a simple two-level quantum mechanics system to the black hole, as I just advertised, I need to make further assumption, of course. Of course, this assumption is with respect to what we already learned from the black hole. The first thing is we know the black hole has a huge amount of entropy, so it must have to account for this entropy, it must have a lot of degeneracy. There's a state called black hole states. So let me just assume the black hole has a states with a degeneracy, with exponential amount of degeneracy, because and then this amount of degeneracy respect so-called area law, because we all know about the area law. So let's make an assumption first. So we have this exponent. So this basically means that the bits, the qubits, the information stored in these bits follow the area law. So the total number of states is exponential of this entropy. S is proportional to A, as we know from the usual black hole area law. So this is a degeneracy G. Usually, you can find this G in the quantum mechanics textbook, degeneracy. And then, of course, the second assumption is because our black hole is in some space, occupied space. So I need to argue that where is degree freedom hiding? Okay, so because I'm talking about Schwarzschild, so that should be a spherical symmetry. So the natural place is somewhere at some radius. So let's say, and usually, okay, outside the horizon. If I get something inside the horizon, then of course I can say something. But fortunately, we got something. Okay, and then this is some degree freedom somewhere outside the horizon. That's the second assumption. In that sense, means what does this assumption do is this? It means when you need to calculate the area. So this is area. When you calculate area, you need to put some. This is area of the sphere. Okay, so this radius of sphere is given by this beta times n. Okay, because we know that in the black hole, the Schwarzschild radius is 2gn. Okay, now we take a g equal to 1, okay, c to 1, whatever, h bar equal to 1. Okay, that's the case. Then we have this beta m. We will find out the beta here later, and we will determine the alpha as well. So those are just some parameter we want to fit this stimulus emission formula to the Perry-Welch common rate. Okay, so before I store into this formula, let us give some hint from this physics behind that why this is possible, why this can give us some feature emission. This is another cartoon picture to show you that the most important thing is for black hole states, for different label. So that's a 2 label. So that's present 2 label. Of course, for black hole there's many labels. So the difference is in every higher label, or the label corresponds to a bigger mass, there are more degeneracy state than the lower mass. That's probably true because you have the area low. So here the cartoon picture just shows that 2 label system. For example, if you have one vacancy in the lower label, then you might have 2 vacancies in the higher label. Okay? And then so that's mimic what happened here in the stimulus emission. You have some photon coming, and it stimulate one of this state in a higher excited state, jump down to the lower states. Could be a B1 state, or it could be the B2 state, jump down to this lower Vikings. Okay, let's say they maybe have this superposition of the 2 states. But anyway, they have a different probability maybe. And so here I just show you that using the direction of the photon to show that they may radiate differently. Okay, that would be the feature. Okay, but of course I intended to do this because at the end of the day, the only feature we can have for the spherical symmetry black hole has to be encoded in the angular information. Okay, so I just intended to show that emitted from different angles that carry the information. So basically you can say that I argue that the feature emission should come from, should due to the degeneracy, okay, and especially the degeneracy difference between 2 labels. That's my first observation. So here actually given this degeneracy assumption, you already see that for different label, they correspond to different mass, then they have a different degeneracy. So imagine now we have only have 3 seats here. We have 5 people coming to fight for these 3 seats. So 2 people cannot get a seat. That would be the feature. Okay, but for black hole case, we'll argue that this microstate should be behaved like a boson-like. So fortunately, all 5 people can get into the 3 seats because they are boson, they are not fermion, but that also carries some feature. All right, so with this saying, let's give some formula properties. One of the formula is most important in this talk. So we have this, I argue that this stimulating emission is equal to the Perry-Welch atomic rate as follows. As I put in this assumption, I just have, okay, back to this formula, and then of course I need to take some limit, okay, and take this limit. We basically this limit shows that this black hole is very large, the radiation compared to black hole mass is nothing, but of course the temperature has to be low as well compared to the initial radiation energy. Then, as you can expect, that all these factor you can divide by A and B and something, and this will be all this 1 can be dropped compared to the first term, and then you got this approximation. And then this approximation, if you carefully, we can separate into also 2 terms. Okay, the first term actually you can easily identify this is just the Boltzmann factor as you have seen at the beginning. All right, and there's a second term here. So my goal is to make both terms look like a Perry-Welch tunneling rate. So in order to make a first term look like a Boltzmann factor tunneling rate, of course I need to make A equal to B, but it's not important because in this case I can always renormalized, so may not be so important. But in order to have the second term here, okay, to have like Perry-Welcher harmonic rate, I need to have this to be 4 pi omega squared, as you can see here, right? 4 pi omega squared, 4 pi omega squared. So, and when you look at what is in this coefficient C or function C, it looks like this. So it actually made of a function of beta. Beta is the parameter of first set. So beta will determine where are those microscope degree freedom located. Okay, so that will tell me how far is this microscopic degree freedom to the center of your black hole. So, so you don't want this term for sure. This is a mixing of n omega. It doesn't show up in the Perry-Welcher. So you only have this term remain. So you have to set this to 0. That gives you beta equal to 1/2. All right. And what is the 1/2 means here? Because you want to have your spherical measure in the usual way. So I'm using this isotropic matrix, which is maybe not so common in this black hole physics, but it's one of these metrics people use. In this matrix, 1/2 is right at the horizon. So I argue that this degree freedom has to be located at the horizon. Okay, although I don't really use any function of the horizon, but it has to be located at that location. Once this first leading term gone away, after I choose beta equal to 1/2, and this second term give me some number, and this number unfortunately is not 4 pi. So I need to determine that can determine the beta. So beta I have to put in 2, so that the second term will be 4 pi omega squared. So the beta equal to 2, representing that each vacancy has 2 degeneracy. Okay, so this basically, then you can have a result. All right. So this is a second. So you got 2 information. It actually got 2 consequences. One is the degree freedom is located at the horizon. Second is each microstates or each vacancies has a degeneracy of 2. It's like a doublet. Okay. I always think about this is in the future. I think about this is like say soft graviton or those kind of boson with spin 1. Okay, so it has or spin 2. So it has a massless and has a degeneracy 2. But we will see to that. Well, in this talk, I will not say much more about this because it's still unclear to me. But this result I get if one would fit the Einstein's linear emission to the PK atomic rate. Okay, now so I have a better idea how to compare these 2 models. So let me just review. Also for me, it's the first time that I'm not studying the quantum optics. James Cummings model is very common and popular in the cavity QED. So this picture I showed you earlier. So it has 3 parts. The first part is a 2-level Atkins energy. Okay, it's using the polymetry to represent such a 2-level states. And then there is in the cavity there is interacting with the radiation or the photon. Usually it's in the coherent states. So that's this green part. So this is the photon energy, as you can see. And then of course they have to have interaction. So for example, the ground state atom receives the photon and jump up, and then the excited states release the photon and come down. So this is described by the interaction with the coupling G. All right, so it's also very straightforward. So these are 3 parts in this James Cummings model. As I mentioned, this is what I just mentioned. And there's other thing here. Maybe it's worth to mention a little bit. This K means even in the reality, the cavity cannot really keep the photon forever. Okay, so there is a decay rate. Eventually, the photon will leak out. That will be represented by this K. And this transition from the excited state to lower state will also emit the photon that is represented by this gamma. Okay, so that's a decay rate of your say dipole moment, because in this model you use a dipole moment as you learn from the quantum mechanics books. Dipole moment to describe such a transition. And there is a T transit here, which means this usually means how the characteristic time this atom survive in such a coherent radiation field. Okay, so this eventually this should correspond to the lifetime of the black hole. If we want to model this as a black hole. Okay, so this is a feature of the James Cumming model, and we're using this model to try to simulate what happened to the black hole and see how close it can get, or what kind of a feature we can get from this model. So let's just make a naive guess that we have a James Cumming model for this cavity black hole system. We have kept the black hole in the cavity, if we can do that. And then we have a black hole. Maybe look at a picture first. We have a black hole, and we know we will get this degree freedom just located at the horizon. And the degree freedom in the spatial representation, it should come into this each of this plateau with a Planck size, right? So then this is degree freedom is with respect to the area low. So of course, we can further imagine in this one of these plateau, they have is a doublet. You have some spin up, spin down, representing this degeneracy 2. So that's the one we obtained earlier using this formula. And so here, the first term we have, before it was a two-level atom energy, now it's a black hole energy. It composed of, and also consider two levels. So let's say we have a level A and level B. Level A is the lower level, level B is the excited level. That's usually first toy model, two-level black hole model. And then, because black hole have a lot of degeneracy, so this IJ index corresponds to the degeneracy, which is exponentially large. And then we also have a photon, right? You put in the cavity, so all the Hawking radiation, let's say the radiation in the form of the photon, so there's a photon bounce back, there's a photon energy in the cavity as well. And then there's an interaction just like we have in the cavity QED, and this is called interaction. And the coupling G, okay, now we have IJ index representing that there might be, if we have a different G for transition between two different states, then there's a feature. Okay, this is where we want to store the information. All right, and this is just the interaction. Okay. All right, and so this is just a straightforward generalization of the James Cumming model. For, you can say, for the two-level, but a lot of degeneracy. Okay. Well, of course, this will not be easily. I mean, this will not cause the interesting for maybe quantum optical people, because they don't really have such a system. And but for us, of course, for me, I think we should start with this one. So, so let's see what happens. Okay, so for example, if we could provide some ground state, okay, and then this is a standard calculation for the James Cumming model. That given time, the evolution will involve a couple of all the states. Okay, in this case, I have two vacancies in the excited state called B1, B2. To represent, I just claim the degeneracy increase once the black hole mass increase. Go to the excited state, they have more degeneracy. So I have two degeneracy of the excited state. I have only one vacancy in the ground state. So easily you can get the later time they will be the mixture, okay, mixed state between these two states. Okay, and then you have with some normalization factors, and you can factor out, come up with this ratio between these two different transition coupling, which is the G here. And in order to have information, I will keep this ratio is not equal to 1. All right. So it's very easy to see at some late time, the distance survived in the red box. Okay, this term is the mix of two excited states with different probability amplitude determined by delta. All right, so that's my observation that this is where you store the information. And so how do we look at these mixed states? Okay, and that go back to this stimulate emission. Stimulate emission usually it's also a model used in this laser physics. All right. So in laser physics, you want to enhance the radiation. One of these systems is called the amplifier or the photon pump. Okay. By doing that, usually you will keep feeding your laser or your resonance some photons. And to study this, you can do this so-called weak rotate or analytic continuation by making this making this coupling G to imaginary. So that will turn your omega, which is usually called a rapid frequency, also to the imaginary frequency. So that will turn your states, okay. This one can be decomposed back to these states, okay? And then this E plus E minus are the eigenstate of your original Jennings-Cumming model. So that will make I here disappear. So make like the coefficient may like some Cauchy and sinh function, hyper cosine, hyper sine function. All right. So because then this is in the amplifier system, this is like a kind of Buchler transformation. And this omega, or omega prime after the linear continuation, can be understood, okay, in the laser system. It's kind of some coefficient which you can identify as some kind of Ulu acceleration, or in our case, it's basically the Hawking temperature. So this omega prime should be around 1/n, which is about the Hawking temperature. Then you have you come up with this states after the we rotate your coupling. Okay, and the reason I want to do this re-rotate is because I already learned that people working on this, okay, a bunch of people here, of course, stuff from Hawking and Schrodinger's, about this soft graviton, okay, business. They argue this BNS transformation of this soft hair symmetry broken at the presence of the horizon that produce Gaussian boson. Okay, the symmetry breaking produce a Gaussian boson. And those Gaussian boson modes is represented by function f. Okay, I referred to this paper. One of the author, Abu, is our postdoc here a long time ago. Now he's a faculty in India. All right, so they have a paper. They try to derive the equation motion for this transformation f. F is a functional is a transformation of this BNS, okay, BNS symmetry. So this transformation has angle dependent coefficient here, okay, and so different feature actually is stored in this coefficient. So the superposition can produce a different transformation. And they have two modes. So if you really look at, well, not carefully, but just look at these two, you can argue that, well, this model is quite naive and simple. version, but if you want to complicate it to become this kind of model, then you can start to argue that they look actually similar. So what I want to say is the delta here, which is come from the coupling between the atom and the photon. Now it's a couple between the black hole and its radiation. Okay, if it has angle dependent, then it will look like what we have of this boson boson. Okay, so this is one observation. I want to say that this is a simple way to write a qubit. Means that if I want to write a qubit with superposition of some steady states in the black hole, I just need to tune. Okay, I just need to input what I want for this coupling. Then I can write this ratio into the amplitude, and this amplitude give me the information. Okay, so that's just a simple observation. And the other observation is as follows. Also come from this Jennings-Cumming models. People work in this field try to study how the entanglement in this model works. Okay, so you can compute something called DEN. I think it's called the degree of entanglement due to mutual entropy. Okay, basically it's a way to quantify the entanglement. And mutual entropy representing this, you will see later. This entropy is can write in terms of some kind of it's a relative. It's a kind of a relative entropy. Okay, mutual is a mutual entropy between the radiation field and the atom. Now it's a radiation and a black hole. So that's a mutual entropy represent. So I want to see how this entangle between the black hole itself and its photon fields, or you say its Hawking radiation. So so you just prepare again. You prepare your this is a density matrix in your initial states, which is given by the two excited states. Okay, so you got some information stored in this coefficient as I mentioned earlier. Okay, you got some mixed states with different weighting here. Say lambda 1 and lambda 2. Of course, lambda 1 plus lambda 2 has to be 1. Okay, and then you can compute how this density matrix evolved with the time. Okay, by apply this Hamiltonian, which I didn't write out, but you get Hamiltonian from here. Okay, Hamiltonian with only simple one state and two excited states. Then this is some quantity compute, and the photon. The Hawking radiation is a photon radiation field. Is in this case I would just assume it's just like a cavity QEDs in the coherent states. You got this coherent factor for the photon, and then you calculate this DN. Is a mutual entropy, and then you draw the picture. So in this case, for different number of photons. So imagine that you have a black hole in the cavity, and you have a 5 photon here is a blue line. You have 10 photon here. You have 50 photon here. Interact with your black hole. So here the picture shows that first you oscillate. This is natural for this model. This is called rapid oscillation. Okay. This is happening because the information will be transferred from the black hole, or from in the whole case from the atom and to the radiation back and forth. So that's called this oscillation. Let's look at the usual feature. The usual feature is it will oscillate, but it will also go up and down. And the blue line here shows that usually it will go to the maximum within some time. Okay, So for example, for 5 photons, you will reach its maximum here around 3 unit of time. For the 10 photon here, you will arrive in this maximum a little bit later, around 5. But for the 50 photon here, you probably reach, it's about around 5, but it's a little bit longer than 5. So as you keep simulate with different photons, you can see this system will achieve this so-called maximum entanglement sooner or later. With interaction with more photons, you will cost slightly more time to achieve such a highest entanglement, but will not differ too much. But the point is, once you achieve the maximum entanglement, for more photons, you will stay longer. Okay? So for the green line here, you can see this entanglement stay very long life. Okay? Larger in this picture anyway. But for like a 10 photon, 5 photons, this entanglement actually will decay rapidly, okay, or something sooner, okay, than this one. So you can imagine that how many photons we have. Imagine a black hole, the huge amount, exponential amount of photons. So this entanglement will survive very long time. Okay. Oh, already? Yeah, okay. This is my last slide. Okay. So here I come to my conclusion. Sorry, I didn't see this. All right. So we have first regard these Hawking regions as stimuli emission. We have 2 conclusions. We got this microstate with double degeneracy sitting at the horizon, which I suggest that would be the DNA symmetry for the graviton. And then I also show that in a simple JC model, the coupling, the angle-dependent coupling, maybe can be encode the information, just like BKS transformation. And at the end of the day, I show that the evolution of the entanglement will survive long enough before this information carried away by the radiation. And I suggest that such a cavity may play by the photon sphere in such a case. So this is my last version of my last picture here. I have a black hole here. A black hole can be characterized by a multi-level, n-level atoms, and they have a double degeneracy for each microstates. And there's a cavity played by the photon sphere here. So they have look like a cavity. And photon sphere, of course, is not a totally refractive wall. So by time the photon can leak out, just like this K, and this T will represent the lifetime of the black hole, and G will be the coupling between the photon and the black hole, and this will be the Hawking radiation. So that's my final picture of this talk. Thank you.
One brief question. Let's speak